Welcome. This session will discuss one of the subassemblies for Civil 3D that was recently rebuilt. The subassembly is our new milling and resurfacing subassembly. I'm Bruce Stana with the Florida Department of Transportation Engineering CAD Systems Office, and Randy Roberts, also of the Engineering CAD Systems Office, will be joining me. The purpose for the milling and resurfacing subassembly is to meet the requirements of the Plans Preparation Manual. The Plans Preparation Manual says that the typical section and details, including the milling and layering, shall be shown in the plans. The subassembly has several options. The options include a constant depth milling, and when you have a constant depth milling, that means you're going to be matching the existing cross slope of the pavement sampled at each subassembly insertion. You can also have variable depth milling, and where variable depth milling occurs is where cross slope correction needs to be made. So in constant depth milling, what that means is you're going to mill down a specified depth and then add an overlay back, which is optional, at a specified depth. You can control the subassembly by using a large sampling tolerance to make sure that the sampled cross slope matches the design or desirable cross slope. In cross slope correction situations, a variable depth milling will be the first option that the subassembly attempts to do to try to achieve the desired or designed cross slope. This is controlled by using a tighter tolerance range on the amount of cross slope tolerance. For example, the exhibits in the Plans Preparation Manual show a plus or minus 0.5% tolerance for the design cross slope. After that 0.5% tolerance, then variable depth milling is appropriate. If variable depth milling cannot achieve the design cross slope, overbuild may be applied. Overbuild is typically a wedge-shaped section of asphalt at varying thickness from the inside to the outside to achieve additional cross slope to correct for an existing pavement cross slope out of tolerance. Overbuild is only applied if variable depth milling cannot achieve the desired cross slope. After an overbuild is applied and if the desired cross slope is met, then a constant thickness overlay is added to complete the resurfacing. Optionally, a friction course of a constant thickness can be applied on top of the resurfacing layer. So the basic flow of the subassembly proceeds as follows as we look at the slide from top to bottom. The first thing that occurs upon insertion of the subassembly is the existing cross slope is measured. The user has the option to measure at the full width of the subassembly as the subassembly parameters are input, or they can sample between the full width using offsets, or they have the option to target feature lines or alignments with profiles in their subassembly. Once the cross slope is sampled, the decision is made: does the existing cross slope match the design cross slope? If the existing cross slope is within tolerance, we'll do a constant depth milling as you see on the left side of the decision triangle because the milling matches within the cross slope, and then the subassembly will add an overlay if that's what's selected with the parameters. If the existing cross slope does not match the design cross slope within the tolerance, then we have to make a choice. The subassembly will first attempt to use a variable depth mill to try to achieve the desired cross slope. The variable depth milling is constrained by parameters such as maximum milling depth and minimum milling depths. If the maximum milling depth constrains the subassembly where it cannot achieve desired cross slope, then the variable depth mill will mill as much as it can within the constraints, and then we'll go into an overbuild situation. But if it can achieve the desired cross slope with a variable depth mill, it will variable depth mill within the constraints specified by the maximum and minimum milling depths, and then a constant thickness overlay can be optionally added. In the situation where the variable depth mill cannot achieve the desired cross slope because of constraints, such as minimum and maximum milling depths, then overbuild is applied. Overbuild is also constrained where we have a minimum overbuild thickness and a maximum overbuild thickness to try to achieve the desired cross slope. If overbuild is applied and it can meet the desired cross slope, then overbuild is applied and then a constant thickness overlay is added. If overbuild cannot achieve the desired cross slope, we're in an error condition and the subassembly writes out an error. In each case, we're going to see, as the subassembly gets inserted, a report of the performance of the subassembly is output that the user can see all of the resulting elevations, depths, areas, thicknesses, and so forth. And that information is output into a comma-separated values file that can be loaded into the plans or manipulated with spreadsheet software such as Microsoft Excel. The FDOT Plans Preparation Manual specifies the typical desired cross slope in a normal crown situation for single and multiple lanes. These values should be the design target cross slope when you're running your subassembly. The subassembly is also sensitive to super elevation and will retrieve super elevation when the section becomes super elevated. In either case, the typical cross slope, such as a 2% or a 3% or even perhaps more percent if that's what the user inputs, can be the target design elevation in a typical tangent section. In super elevation, the design cross slope is read from the super elevation parameters within Civil 3D. We've described the performance of the subassembly diagrammatically, and now we're going to show you how it actually works, and it's probably best to show you in the form of a schematic. I think it's pretty straightforward to understand how a constant depth milling and constant thickness overlay works, but it's probably a little more descriptive to go ahead and start maybe with a variable depth milling. First of all, this line that's in dashed here represents existing ground or the existing surface that's going to be sampled. When the subassembly is inserted, it's basically inserted at a point. That point is usually a profile grade line that is defined at an existing surface. So when you're targeting, the subassembly is going to insert just like a normal subassembly would. If you want all of your milling operations to start at the existing ground, you'd want your profile grade line to be designed right at existing ground. So you may do a existing profile right along the top existing surface of the earth. The behavior of the subassembly, however, is it will begin milling operations at wherever that insertion point is and begin milling down. But a second thing to note in the behavior of the subassembly is that a friction course is always added to the top of the overlay. So if you do have a friction course, say of 3/4 of an inch, you may want to calculate your profile 3/4 of an inch below your existing ground and begin your milling from there. This seems a bit odd, but since friction course is optional, that's the way the subassembly had to be written. So if you know you're not going to be adding a friction course, run your profile grade line right at the existing ground. And if you're going to have a friction course and you desired the finished elevation at the top of the friction course to match the original elevation of the subassembly insertion, you would want to run the subassembly at a slightly depressed elevation below the existing ground, matching the thickness of the friction course you intend to apply. So in a variable depth milling situation, basically, that is where the existing cross slope is out of tolerance with our proposed cross slope. In the example we show here, the existing ground is slightly flatter than the 2% desired cross slope. And if the existing was flat enough and outside of our tolerance, it would warrant a variable depth milling. So what's going to happen is the subassembly is going to insert, and in this case we're going to insert directly at this point. We may have our minimum milling depth set to 1 inch that is shown here in the diagram, so the milling would always have to go down at least 1 inch if that's what we had set with our parameters. And then in this case a variable depth mill will occur until the 2% design cross slope occurs. So the milling would look something like this. So the area we see shaded in yellow becomes our milling area, and then once that desired or design cross slope is met, a constant thickness overlay is applied. There's a parameter that's set to yes or no. If the parameter's set to yes, and we'll look at the parameters in just a few moments, it will target back to that elevation. So you will not have to control exactly what the thickness of the overlay is. The overlay will always target back where it meets that insertion point elevation. If you have the parameter set to no, whatever the thickness of the overlay that you specify in the subassembly will be met. Things get a little more interesting in variable depth milling. Remember, in variable depth milling, and in cases where we might have to have overbuild, sometimes our design cross slope cannot be achieved with milling alone. So the way the subassembly works is, again, it will sample the cross slope of the existing surface, and optionally, as we mentioned, you can sample inside of either the width parameter that is set, or if you are using targeting, such as targeting a feature line or targeting a alignment, you can offset to the inside of those targets to sample the cross slope. The sampling of the cross slope only samples down to the slope and uses that for the existing cross slope. In this case, it's not going to sample down here, but it would sample from the width in or outside of that width, in or outside of that width, and that is only used to determine what the existing cross slope is. It has nothing to do with the width of the lane or anything like that. So in the case where we might have variable depth milling and overbuild, the desired cross slope does not match our design cross slope that we have here. So what will happen is we will sample, the subassembly will determine we are outside of tolerance. It's going to do a variable depth mill to try to achieve the design cross slope within whatever constraints we have on the milling, like a minimum or maximum milling depth. In this case, of course, this depth would have to be tested against our maximum depth, and this depth would have to be tested against our minimum depth. But if our depths, minimum and maximum, constrain how much it can variable depth mill, it will then have to revert to an overbuild situation to achieve our design cross slope. So then the subassembly then applies an overbuild like we see in the green shaded area, and that overbuild has to match a minimum overbuild thickness and also must stay within a maximum overbuild thickness that we set as parameters. And in this case, the minimums and maximums allow this wedge-shaped overbuild section to come in and have the desired cross slope be achieved. Finally, we apply a constant thickness overlay. In this case, you see right here, the constant thickness overlay does not come back to our minimum elevation, because when we inserted this subassembly, we actually had the subassembly track below the existing ground by the thickness of a friction course that I'm now going to apply. So once the friction course is applied, we have the friction course at our desired cross slope, and the top of the friction course matches the top of the existing surface. On the FDOT subassembly tool palettes, you'll see a tab called 3R, and the mill and overlay match slope is a subassembly that we want to run. The mill and overlay subassembly is just like any other subassembly in Civil 3D, that it's inserted in the assembly either on the right or left hand side. The side parameter is the first parameter in the list as a default, and you would switch that left or right depending upon the side you wish to insert the subassembly. Note that in Civil 3D you can also drop the subassembly either on the right or left hand side, and that parameter should shift for you. The pavement structure width is the desired width of the pavement structure which you are going to mill or overlay. That value by default is set to 12 feet, but it can be set to a smaller or a larger value depending upon the width of milling and the width of pavement that you wish to operate on. Note it is very important to set that to a value less than or equal to the width of the super elevation that you have calculated. So if you've only calculated the super elevation to 10 feet wide but are trying to do a pavement structure width to 12, the subassembly cannot read the super elevation from Civil 3D. So it's very important you calculate your super elevation properly against your alignment and make sure that your pavement structure width is equal to or less than the width of the super elevation calculation. Note that that pavement structure width can be a fixed value, or it can target offset alignments or offset feature lines and profiles along with the alignments. The use offset sample points variable is used to determine whether or not the sampling will not take place at exactly the insertion point or the value of the pavement structure width. The sampling points can cause the actual elevation sampling of the cross slope to take place either more narrow or wider than the pavement structure width. The inside sample offset offsets the sample point either left or right of the insertion point. The outside sample point offsets the sampling of the elevation either inside, left or right, or outside the width parameter. The inside sample offset is used to offset the elevation sampling of the existing terrain either left or right of the insertion point. A negative value will offset to the left and a positive value will offset to the right, more toward the center of the milling. The outside sample offset performs the same way, except it's checking where the sampling occurs either at the target or at the value of the pavement structure width. The desired slope parameter is the desired cross slope of the pavement. This value is used when super elevation is not used to derive the pavement cross slope. Note that in Civil 3D, super elevation is calculated in both tangent and in curved sections. So if super elevation is being used, the actual super elevation determines what the desired slope is. If super elevation is not used, the desired cross slope value is used. Here we have the desired cross slope set at a very typical value of 2%, which would be the normal cross slope of a typical 2-lane roadway. You can change that value to whatever value you need to achieve the desired cross slope if super elevation is not used. The desired cross slope has a tolerance value. Here we have the tolerance, the allowable upper slope tolerance and the allowable lower slope tolerance set to 0.5% each way. Therefore, if we had a cross slope of minus 1.5% or a cross slope of minus 2.5%, we would be within tolerance and we can have a constant depth milling. If we wanted variable depth milling, we could tighten down on our allowable cross slope tolerances. Or if we always wanted to have constant depth milling, we could set the allowable upper and lower slope tolerances to much larger values and we would always achieve a constant depth milling. Again, variable depth milling will be attempted if constant depth milling is outside the slope tolerances. The super elevation is the next variable that is set. Here it is set current side, inside lane for super. If you did not want super elevation to be used, there is a setting that can be set from the pull-down list that says do not use. In that case, the desired slope variable would then override and the desired slope would be used for the insertion of the subassembly. But if you wanted design or desired cross slope to be calculated from the super elevation, you would set the super elevation parameter to the appropriate variable in the desired super elevation pull down. Mill depth is the next variable. This is our standard depth of milling. We set that if we're going to do constant depth milling. Note that the mill depth is set to a static value, and this is the value that will be milled if constant depth milling will occur. Again, constant depth milling happens if we are within our allowable upper slope tolerance and our allowable lower slope tolerance of the design cross slope. If we're outside the allowable upper and lower slope tolerances, we're going to get variable depth milling, in which case the mill depth is going to be ignored. In variable depth milling, the milling is controlled by the minimum mill depth and the maximum mill depth. Again, the mill depth, min mill depth, max mill depth creates the milling envelope in which all overlay and all overbuild must perform. In variable depth milling, the minimum mill depth specifies how deep the minimum amount of milling must occur. The maximum mill depth specifies the maximum mill depth below the existing elevation that the subassembly is allowed to mill. Note you want to set the maximum mill depth to a large enough value, but not too large that you will mill into the base. Likewise, you want to make sure you set the minimum mill depth to a value deep enough to make sure you remove any bad material. If variable depth milling cannot achieve the design cross slope, then we're into an overbuild situation. Here we have two variables, minimum overbuild thickness and maximum overbuild thickness, that specify the thicknesses on the right and the left hand side of the overbuild wedge of asphalt. You want to set the minimum overbuild thickness to a value large enough that you don't crush the aggregate in the overbuild. Likewise, you want to set the maximum overbuild thickness to a value smaller than your milling envelope. Here we have the maximum overbuild thickness set to 1, but yet our maximum mill depth is set to 0.67. This would not create a very desirable situation in most conditions, especially if we had a very drastic cross slope we were trying to correct. So generally you want to have your maximum overbuild thickness less than your maximum mill depth, so your overbuild stays within the milling envelope. The overbuild is always added on top of the milling, and the overbuild condition will only occur if variable depth milling cannot achieve the desirable cross slope. The next variable is overlay thickness. Overlay thickness is used when we are trying to do a constant thickness overlay. There's a variable called hold overlay at anchor point elevation that, regardless of variable depth milling or variable thickness overlay, to make the overlay achieve the same elevation of the insertion point. Here the value is set to yes. So with that value set to yes, after we do variable depth milling, or even in constant depth milling, it will attempt to put the overlay elevation back to the same elevation as the insertion point. If that value is set to no, then the overlay thickness parameter is used, and we will get a constant thickness overlay of 0.33 in the case of the dialog. If we have that set to yes, that means our overlay target back to the elevation of the original insertion of the subassembly. Normally this parameter is set to yes, but you can override that by setting the parameter to no, and then controlling the thickness of the overlay by changing the overlay thickness, overriding any variable thickness. Note that if you do set that hold overlay at anchor point elevation to no, the overlay will always be added at the overlay thickness, and the overlay thickness will be at whatever elevation it happens to be at the end of the calculation. The next variable is flip super elevation from target. This variable is used when we have multiple lanes and our cross slope is changing, typically in 3 or more lanes of cross slope with travel in one direction. What this allows you to do is to pick up offset alignment to use that for your super elevation. So for example, let's say we had 3 lanes, we could actually use the targeted outside lane alignments super elevation to control the super elevation and the value of the cross slope for the insertion of the subassembly. Ordinarily we would have this set to no, but if we had 3 or more lanes and we had a controlling outside alignment, we could set that to yes, and then the targeted alignment for the outside-most insertion of the subassembly would be used to derive the super elevation. The next couple variables help us look at the behavior of the subassembly in layout mode. When in layout mode, you can change the value of a virtual cross slope and see how the subassembly is going to behave. And in real time, the layout will update showing the behavior of the subassembly. This does not affect the subassembly at runtime. Likewise, we can also delta elevate the insertion of the subassembly from the surface and see the behavior of the subassembly in layout mode. Ordinarily, you will not have to adjust these values. The next 2 variables, mill and overlay geometry log file and air log file, create subdirectories under the folder name of the drawing by the name of the corridor and create a CSV and a text file as you see below. The mill and overlay geometry log file and air log file name are used to look at the performance of the subassembly after it is run or after the corridor has been computed. The ampersand CORR variable picks up the name of the corridor and builds a subdirectory beneath the directory of the drawing file that you're running the corridor in. So if your corridor is called ABC, then the subdirectory that it creates is going to be called ABC. The name of the log file will inherit the name of the subassembly underscore geometry log.csv. This log file logs all the output of the subassembly in a comma-separated value list that can be brought into a spreadsheet like Excel and cleaned up and reported on. Likewise, if there's any errors running the subassembly, an error log file name is created, again with the corridor name as the folder built beneath the directory that the drawing is in, along with the subassembly name, and appended to that underscore errorlog.txt.
Now that Bruce Dana has explained the parameters and how the milling and overlay subassembly works, let's take a look how it works inside the drawing file. Currently, we have a file. It's broken into 2 viewports. The top viewport, you can see a profile. You can see a plan view, has a surface, a sample line group, and I have made some section views that we will insert the finished corridor so you can take a look at how it lays out. To begin with, let me explain. On the bottom viewport, we have an alignment that is promoted into the file. Every object is promoted into this file. We do not have any data shortcuts for simplicity. The alignment is where you will have your super elevation calculated. If you have a data shortcut, you would have your source file with the alignment that you would have to go and run all your calculations on, save that file, and your corridor file updated with a little balloon notification that your reference has been updated. But we are going to do it straight in this file. So let me show you the alignment properties. Is where you're going to set your design parameters. Highlighted the alignment, and there's a contextual ribbon on top, and we can pull down the super elevation, calculate edit super elevation. This is going to pull up your parameters, design parameters. Currently on this one, we have a design speed of 70 miles an hour. We're going to do an extreme case scenario with the milling and overlay, so you can see some real reaction. It's not a real world design, but it will give you a good idea today of how this will look. So we have the super elevation wizard, and let's just run through it and recalculate the alignment. So I'm going to select the entire alignment, and the wizard comes up and we walk through based on the road design that you're working on. This one is an undivided crown, so we'll just walk through. Next, we're going to be doing a 10-foot lane, so we're going to leave this at 12 foot. That gives us plenty of room to show our design. Go through next, and we're going to use the Emax 10% for maximum effect. Once you select your parameters, select finish, and what comes up next, you can see how the super elevation looks. What we're going to be looking for is a max super, a full super at 10%. So at this point I can close this out, and it's giving you a warning here that we're out of range and the radius for the curve. That's okay. So this is the extreme version. We'll close this, and now we're ready to lay out our assembly. Okay, on your tool space, you can cut on your tool pallets, and your assembly pallets will appear. We want the RRR FDOT pallet. That's where our milling and overlay assembly is. Our first step is to go back to Home tab, click on Assembly, create Assembly, and we'll give it a name. In this case, we're going to call it Milling Extreme. Undivided Crown Road FDOT style. For code set style, we will use FDOT X section mill. Select OK, and on your command line it's asking for the location where you want to put your assembly. Just click anywhere on the screen, it'll zoom into it. You can click on the tool palette, click on mill and overlay match slope, which is our milling and overlay subassembly. Click on it, and a box will come up where you can enter in your parameters. Going from top to bottom, let's make some changes on the parameters. We want to change the pavement width to 10 feet. We want to change the use offset sample points to no. We want to leave the mill depth at 4 inches, which is 0.33. The minimum mill depth, change it to 1 inch, 0.0833. Max mill depth, 8 inches, which is 0.67. Minimum overbuild thickness, we want to put 1/4 of an inch, which is 0.0208. Maximum overbuild thickness, 4 inches, 0.333. Overlay thickness, 4 inches, 0.33. And friction force thickness, 3/4 of an inch, which is 0.0625. All the other parameters look good, and out of habit, I'm going to change this to the right side. Move this out of the way. And looking at your command line, you can see it's still waiting on you to pick the assembly, the marker point. Click on it, and it'll insert the right side. Change it to left, and click on it again. We have several styles that are associated with assemblies. The style that this one is currently at, selected FDOT X section mill. Now this is the production style. You can switch this style over to FDOT assembly. Now this will give you a good layout mode look of what's going on. And if you select a side, you also have in the parameters an option to change the percent and layout mode virtual surface, so you can see how the assembly will react in layout mode. And as you can see, I changed it to -5%. Okay, with the virtual slope set to -5%. Let me hit escape so you can see the colors better. The cyan vertical lines represent milling. The blue crosshatch represents overlay. So you can get a clearer view of what's going on and how the subassembly is reacting. So let me just switch that back to where it was. Let me change the style back to X section mill. At this point, we're ready to make a corridor based off of this assembly. So let me close properties, go to Home tab, click corridor, give it a name. We'll call this Extreme Corridor. Corridor style FDOT. Alignment, there's only one. The profile, existing, and assembly. We want the milling extreme. We select our target surface, which is the existing surface, and select OK. And it brings up our frequencies and targets that we can set. In this instance, we're going to change from 25 feet the tangents, curves, spirals, profile curves from 25 to 100 to expedite the processing. And we'll select OK. Our alignment, our profile, everything looks good. Select OK. It's going to ask to rebuild the corridor. You see along the bottom, it's working in the background. Okay, let me zoom out of the top viewport. Let's zoom in. We should have our extreme corridor present. Let me go over one of the options. We are targeting the existing ground. The top of the overlay, which is right here, is targeting the existing ground. And if you have a friction course, keep in mind that if you want the existing ground at the top of the friction course, you have to offset your profile, the thickness of your friction course, to get the top correct. So to clarify on this assembly, as it currently is set up, the friction course is going to be on top of the profile, on top of the insertion point. Let's take a look at our corridor closer in section editor so we can see it more clearly. Have it selected. You can, on the contextual ribbon, select section editor, and you can walk through station by station. So let's take a look at a station and see what we have here. Within section editor, you can hover inside the shape and it will tell you what shape code it is. In this case, we're looking at the milling, which is the cyan color. We hover in the overlay section, it's blue, and of course the friction course. And the data also shows the area at each section also. Now this only shows this information in section editor. Here we have skipped to station 161 plus 00. Here you can see milling a little bit clearly. It's going all the way down to the bottom of the milling, then building back up with overlay, which is underneath the milling. Can't see it there. And then the friction course. As we look through section editor, you may find that where you expect to see super elevation, there's no reaction. We made an error in one of our parameters, and when you run across this, you need to make this change. So we'll close section editor, go back to we'll select a side of an assembly, go to properties, and we want to change the desired super elevation parameters to current side outside length on both the right and left. And then we can close properties, go to our prospector, look at our corridor or extreme corridor, right click, select rebuild. Alright, let's see what happened again when it rebuilt in section editor. I know that we have super starting right now. Alright, looking at this station 161 plus 49, we have the right side that is in super, that it could achieve the results that we put in, the parameters. We zoom in, you can see the green line represents the existing grade, and it is milling down to the bottom of milling. It is then putting in a magenta shape, which is overbuild, putting in an overbuild wedge, and then on top of that, it is doing the overlay to get us up to the desired slope, and then it has our friction course on top. If you'll notice that the left side is missing, when that happens, an error has occurred and it could not achieve the results that we were looking on the left side. We'll go over the error log and show you what happened shortly. So you take a look at the volume output file and the error log, if an error log was generated. Go to Windows Explorer and navigate to your project folder. Inside your roadway folder, there will be a corresponding folder name to each corridor that you have created in the file. So in this case, we want to look at the extreme corridor folder, and we have two files. We have a text file and a CSV with the volume, the geometry log. So let's look at the error log first. And if you want to find out what happened, It will tell you what geometric failure happened for instance, at station 161 plus 00 on the left side. It couldn't achieve the required delta mil. That seems to be the only thing wrong with that. Is you can go through and see what other errors occurred. So that's your error log. On your geometry log, okay, let's take a look at the format of our geometry log. We have your corridor name, your baseline, your profile, and your side, left and right. And 4-lane would have 2 lefts, 2 rights, so it would be formatted as such. You have your station. You have your insert offset. If you pick that parameter, you have your insert elevation. You have your inside horizontal offset and your inside horizontal elevation, and your outside horizontal offset in this case, which is the lane width. The labels are a little out of kilter currently. You have outside horizontal elevation, your sampled slope of the existing grade, and then you get into your depths that it achieved. You have your inside mill depth, outside mill depth, your friction course thickness, inside overbuild depth, outside overbuild depth, your desired slope, your actual overlay thickness, and then wrap it up with the areas. You have your mill area, overbuild area, overlay area, and friction course area. And this is in Excel, so you feel free to format away on your precisions to whatever you desire. One other little tip that you may want to use, as you can see in this table, we have a lot of stations. Now, you may just want to see every 100 feet. So if you want to accomplish that, let's close this table, and we can save it, because it doesn't matter if you save it or not, because you're going to overwrite it if you're going to create a new one. So let's go back to our corridor properties and go to parameters and go to frequency. And all of these options that currently say yes, you want to change to no. We'll leave the super elevation critical points. Let's change all of the options to no that are currently yes. That will be, it'll make the report only go, it will respect the 100-foot frequency. Hit apply, rebuild. As you'll notice, it generates a lot quicker. And let's go back and look at our new geometry log. As you see, it's a lot cleaner and a lot less data. So you can control how much or how little data you want to see in this report. All right, one other thing we want to show is for the sake of time for this video, we've created a new assembly with more forgiving parameters. You can take a look at those. There's a couple of changes that we made on the parameters of the milling overlay 2-lane assembly. We increased maximum overbuild thickness. It is now 10 inches. And we decreased minimum mill depth to 0. And all right, with those steps completed on the assembly with the more forgiving parameters, you can go ahead and create a new corridor. We've already, for the sake of time, created one, and it's called milling 2-lane to match the name of our assembly. And there's one other step that you must do to have labels on your final production cross sections, and that is you need to bring in the point label assembly. And all of this is going to do is create slope labels and elevation labels. And let me close the properties. I will show you where this assembly is. Go to the top assembly tab, assemblies FDOT. There's existing features and point label assembly. Just click and drag it over. And I can close the properties. Parameters are going to be preset. You don't need to change anything. I'm just going to drop this as an example of how I got the other one. You can do a little modification here What you're going to need to do is select the assembly, go to the assembly properties. You're going to need to change the style, the display style of this assembly. So select it, right click, properties, and change it to X section typical, and all the labels will turn on. And from here, you can either run this assembly as a corridor. You will call it, in this case, we call it milling labels. But you can run it as it is. And then, as I'll show when we make our sections, you can delete a few of these labels that you could take out. For instance, the PGL left and right, and you can, when you take out the baseline without taking out the center line, and update your corridor and update your live sections to get the finished look and data that you want. But I'll go ahead and delete this one because I've already inserted one and have already generated the corridor milling labels. And at this point, we can now close properties. We'll switch up to have sections already cut off of our sample line group. To bring this data in, select a section view, go to sample more sources, and here you can insert your multiple corridors. If you have multiple, you want to see how they look in the section views, the production views, you can insert them. So in this case, we want our milling 2-lane and milling labels. And let's make sure our styles are set correctly. We want FDOT existing for our existing profile. Milling 2-lane is our production FDOT X section mill, and milling labels X section typical. Click OK, and our section should fill in with those two corridors on top of each other. And here we have our lanes and our slope labels with our elevation at the edge of your lane, edge of travelway, and this is your existing grade elevation. If you accidentally run your point label assembly after you have already created sections and inserted your production milling and overlay assembly corridor in, you have to erase your section views, go through the Create Multiple Section View wizard. The only change you need to make on the elevation range is change from automatic to user specified, follow a section, and pull down the select section, select milling 2-lane, and at that point continue as you did before. You create your sections, and both the labels and the milling 2-lane corridor should appear.